So in the today's wave propagation, we'll see the topics that you can find out here. That is the wave equations you can see and the type of uniform plane wave. It is also said to be the transverse electromagnetic wave. And we'll see some of the parameters when the wave is propagating in any medium. You can characterize the wave propagation using these constants like propagation constant, phase velocity, and the intrinsic impedance. So first thing, before defining the wave propagation in any medium, we should understand what is the time varying Maxwell's equations. So in the last class, I already told you one of the Maxwell equation, that is the Faraday's law. So what is the Faraday's law says, if you remember? So the time rate of change of magnetic field is going to create an induced EMF. So if you remember it, so that is something like this form. Integral E dot dl is equals to minus whatever I can say, the induced EMF is basically equal to minus d phi by dt. So if you are writing in the vector form, so you are getting curl of E is equal to minus dou B by dou t. So this is one equation which says that, if you recollect the significance of this one, the time variation of the magnetic flux density is produces the spatial variation of the electric field. So one equation we already seen. Now we will start with the other Maxwell's equation. So that got changed from the static fields. That is a modification of your Ampere's law. So can you tell me what is the Ampere's law says? You remember? So what is the equation for the Ampere's law I have given in a vector notation? You can speak out. What is the Ampere's law in vector notation? Am I audible for everyone? You can reply at least. Am I audible? My voice is clear or not? Are you able to listen? Oh, then why you are not replying? Since so many times I was asking, you are not able to reply. Okay, fine. So what is the Ampere's law in vector form? For static fields, what is the equation you have studied? So the curl of the magnetic field intensity is equal to the current density. So this is what the Ampere's law what we have studied, right, in a static fields. Okay, let us start with the static fields. And you know that one of the vector identity which says the divergence of the curl has to be always equal to 0. So what is the meaning of that? So when you are finding divergence of curl of H, which has to be equal to 0 using your vector identity. Okay, what is the meaning of that in that case? So in case of static fields, the curl of H value is equal to J. So which says that the divergence of the current density will be equal to 0 when you are doing it in case of a static fields. So I will consider this one as an equation 1. Now, what will happen? Suppose if you have a conductor, you can see here, this is a conductor. If I apply a time varying voltage across this conductor, so when I apply voltage across any conductor, you can see that there is a current flow. So when I apply any voltage across this conductor, you can see that exactly there will be a time varying current. As long as the voltage is varying with respect to time, you will also get the time also varying with respect to current also varying with respect to time. So in that case, what will happen? So that I can call it as a displacement current. Basically, I will tell you what you mean by displacement current. So how to define the variation of that current? So the basic definition for current is the negative rate of change of the charge with respect to time. So whatever this negative sign actually indicates that the flow of the charge decreases with increase in the time. So that is what the basic definition for the current. Now we will use the same equation and you try to write down the current in terms of the current density. So we have seen in the types of current distribution, the current I can also be expressed as the double integral J dot ds. Now you can see here, since the loop is closed, I can calculate the current as something like this, double integral J dot ds, where the surface is closed here. You can see here, this is my surface which is closed, is equal to minus d by dt of Q can be written as triple integral rho v into dv in terms of volumetric charge. So you can apply the divergence theorem. So what the divergence theorem says? So whenever the surface is closed, you can convert the closed surface integral into a volumetric integral. So what you can say here right now, triple integral del dot j into dv is equal to, so d by dt I can straight away apply for rho v. So in that case, what you will get, triple integral minus dou rho v by dou t into dv. So up to this, any questions you have? So in static fields, your divergence of your current density is equal to 0. But when you are going for the time varying fields, what you are getting? The divergence of the current density is equal to the rate of change of the volumetric charge. So there is an equation changed. So whenever this equation changes, your Ampere's law also correspondingly it has to be modified, right? So in case of a static fields, the divergence of the current density is 0. Explain the last second equation. So you mean this equation? So what I was saying was, see, when you apply any voltage across any conductor, there will be a current flow through this conductor. So since it is a closed surface, I can categorize it as a volumetric current density, right? So how to express the current in terms of volumetric current? So we have seen the current distribution, right? If the line current is I, in terms of surface current, you can express it as K into delta Y. And in terms of volumetric current, you can express it as double integral J dot delta S or ds. So the same rule I have applied here. Suppose if the surface is closed and the current is flowing through a closed surface, so the current I can be written as double integral J dot ds, and this is a closed surface because it is having some volume. So equal to whatever the charge it is there can also be written in terms of the volumetric charge. The reason being why I was converting into volumetric was here the current also you have converted into volumetric current density. Proportionately, the charge also can be expressed as a volumetric charge density. Then I can get a relation between the current density and the charge density. So if you apply the divergence theorem now, this surface integral can be converted into the volumetric integral. So you are going to get this equation. So by comparing this, what is the thing you are getting now? Del dot j is equal to minus dou rho v by dou t. So if we compare that, what is the equation you got? Del dot j is equals to minus dou rho v by dou t. Actually, this is a generalized equation, but when it comes to the static fields, why you are getting del dot j is equal to 0 was. So when I say in a static, what do you mean by static? There is no variation of any charge with respect to time. So which means that your rho v is independent of time. Rho v is not a function of time. Or in other words, rho v is simply a constant number. So there is no time variation of the volumetric charge because what you are calling it as a static field. So whenever rho v is constant, your dou by dou t term will be equal to 0. So that is the reason why when I was going for the static fields, I said that the divergence of the current density will be always 0. And hence, even your Ampere's law is also satisfying. So because J can be written as curl of H using your Ampere's law. So both are satisfying because your volumetric charge density is constant there. Right now, what is happening here? The volumetric charge density is flowing with respect to time. So when you apply AC voltage, the charge flows with respect to time. So there is a variation of the charge with respect to time. That is the reason why I have modified this equation something like del dot J is equal to minus dou rho V by dou T. So this is also called as continuity equation. So the divergence of the current density is the negative rate of change of the volumetric charge density. Now I can rearrange this equation something like this: del dot J plus dou rho V by dou T, or in other words, different way I will write, sorry. So I can say del dot J is equal to minus dou by dou T of. So using your Gauss law, rho V can be written as del dot D, the divergence of the electric flux density. So I can say del dot J is equals to del dot minus dou D by dou T, right? Because del is a function of space, which is not a function of time. So only the electric flux density will be a function of time. So I can apply dou by dou T straight away for D. Now you bring this down to the left side. So what you are going to get, del dot J bar plus dou D bar by dou T is equals to 0. Now this same thing I can express it as something like this: del dot curl of H. So that means the divergence of the curl of a vector is equal to 0. So right now when you compare these two, what is the modification in the Ampere's law you got right now? The curl of the magnetic field intensity is not only the conduction current density, it is also the rate of change of the electric flux density with respect to time. So when I compare the Ampere's law right now, the curl of H can be expressed as the current density J, which is basically said to be the conduction current density, plus dou D by dou T. This is called your displacement current density. So the Ampere's law has been modified when you go for the time varying fields using this equation. So actually, if you can go back from this same equation, you can go back to the static fields also. So in static fields, there is dou D by dou T will be 0. So you are straight away getting curl of H is equal to J. But whereas in time varying fields, there is a change of flux with respect to time that also causes for the some additional current. That I am calling it as a displacement current. So any questions here you can ask now. So do you have any questions? Yeah. So now I will summarize it here. So what is the condition you are getting? The curl of the H magnetic field intensity when you go for the time varying fields is basically the conduction current density plus the displacement current density. So let me call it as JD. So I will tell you why the name comes like a displacement current density. You can consider an example of the parallel plate capacitor. And when you apply a voltage across it, so when the voltage is varying with respect to time, what will happen? There is a change in the current also. Correct. Now, in the case of capacitor, whatever the current flow through this wire, you can call it as a displacement current. So why I am calling it as a displacement current was because if you see the AC voltage, it is continuously varying with respect to time. So at T is equal to 0, the number of electrons accumulated on this plate will be 0. And what will happen when you go to T is equal to T by 4? There is a maximum number of electrons which are accumulated on the surface. So what happens there? The charge density is varying with respect to time. So T is equal to 0, the density of the charge on this plate is less, and T equal to T by 4 it is more, and again T is equal to T by 2 it is 0. So continuously there is a displacement of the charge from the source to the plate. So when you apply any voltage here, there will be some amount of the charge which is induced. So that is the displacement of the charge from the source to the capacitor. So that is the reason why whenever there is a change of charge with respect to time, obviously we'll have a current. So since this current is due to the displacement of the charged particles from the source to the capacitor, I can call that current as a displacement current. Okay, now this is your modification of the Ampere's law. Repeat. So in case of a capacitor, when you apply any time varying voltage, the displacement of the charges from the source to the capacitor is getting varying with respect to time. That is because if you apply any voltage across any capacitor, at time t is equal to 0, the voltage is 0, which means that there will not be any electrons accumulated on each plate. So what will happen at t is equal to t by 4? At this particular point, there is a maximum density of electrons which will be accumulated here. Positive here, negative here. Similarly, as the time progresses, you can see here the density of the charges will be continuously varying. So in other words, how these charges are accumulating, which means that there is a displacement of electrons from the source to the capacitor which is flowing back again. So the electrons are moving from this source to the plate and again coming back. So whatever the current that is created in the capacitor is due to the flow of the charge with respect to time. Because in this case the charge is not a constant and charge is varying with respect to time. So that actually causes for the current. So you can call this as a displacement. Why? Because this is a movement of the electrons from source to the capacitor. So that's the reason why I was calling it as a displacement current. So ideally speaking, if you see here the conduction current density, so the conduction current density, you can call it as a basic Ohm's law. When your EDC will study, the conduction current density is also said to be sigma times E. And your JD, what I called is a displacement current density. Just now we have seen that is a variation of the flux density with respect to time. So which is also said to be epsilon times dou E by dou T. Any questions here? So if I summarize now, the Maxwell equation has been modified something like this. So curl of H is equal to JC plus JD, both conduction current as well as the displacement current. And conduction current you are going to get sigma times E. This anyhow you will see in your EDC. Then you can understand what is the convention current and conduction current, both are same. So the conduction current is basically the change in the potential is to create a current flow. So that is basically called your conduction current density, which we are not bothering about at this particular moment. And the displacement current density is the flow of the charge with respect to time. So that is dou D by dou T. So the Ampere's law has been modified accordingly like this. So similarly, if we see in integral form, so for static fields, what you had, integral H dot dl is equal to I. Right now, the same equation can be modified by adding another displacement term. So it is also called as a conduction current, and this is said to be the displacement current. Any questions here? Or otherwise, let me give one more example for this also. Suppose if we have a current carrying wire. So let me say this is my current carrying wire. I was applying both DC current as well as the AC current. What will happen to the magnetic field generated by this? So that means, can you tell me now?
Sir, that capacitor you are giving example there, displacement current, is it not same
Hmm.
like conduction current? Because conduction current it is happening due to change in potential due to current
Okay.
flow. So
Okay.
current flow means flow of charge, and that
Okay.
cause potential difference. So
Okay.
that conduction current it is not same like the displacement current.
Conduction current is not equal same as the displacement current. Conduction current means, simple example I will give you. Suppose you have two plates. I'm not considering parallel plate capacitor. Okay. You don't confuse about that. I
Mm,
had two metal plates. Okay. It is at a
mm,
potential of 10 volt. Okay.
yes.
And the other one is at a potential of 2 volt.
Okay.
Okay. in that case, what will happen? Suppose in between these two, if the medium is starting conducting, so what you are going
Okay.
to get there in that case, the potential difference divided by the distance is because of this potential difference, there will be a current flow, right?
Yes. Yes.
So in other words, what I can say, in case of a capacitor, the dielectric is causing for the current, right? So what you can call
Yes.
is a leakage current.
Okay.
That leakage current can be called as a conduction current. Why? Because the leakage current generally in between in a parallel plate capacitor will be a dielectric is present
Yes.
between the plates, right?
Yes.
Ideally speaking, the dielectric conductance has to be infinite. So I mean resistance has to be infinite. It doesn't allow
Yes.
anything, right?
Mhm.
But when you consider the practical cases, it will possess a finite conductivity.
Okay.
Right. Ideally cases, if you see here, your sigma will be zero. Dielectric should not
Okay.
conduct anything. But what will
Mhm.
happen when you take a practical dielectrics? You are having a
That,
finite conductivity. So because of the conductivity of the dielectric, there will be a current flow through the medium, through the dielectric medium. That you can call it as a conduction current.
okay. That means without source it can happen. There is no
Without
need
source,
of.
it can happen if there is a potential difference.
Yes. Yes. It is charged already.
Yes.
Potential.
So some simple
Okay.
example also I can give you. Your DC current, whatever I was talking about, conduction current can also said to be the DC current in some cases. See,
Okay.
suppose I have a parallel plate capacitor, okay, and I have applied a DC voltage, this 10
Yes.
volt, okay.
Yes.
Now in this case, whatever the current is flowing through the dielectric medium, this is basically called your convection current or conduction current.
Okay.
Ideally speaking, your for DC, your capacitor has to be open circuit. That is what theory says.
Yes.
But in practical, what will happen? This, whatever the dielectric present between the conductors, is start conducting because finite value of
Uh, Okay.
ideal dielectric should have conductivity zero, which should be non-conducting medium. But
Yes.
still, if you take the practical dielectrics like ceramic, paper, all these are dielectrics, right? They
Right.
will have a conductivity which is equal to zero, but close to zero.
Okay.
You got my point?
So
Because of
and
that conductivity, even if you apply a DC voltage also, there will be a current flow. Yes, the circuit is closed
okay.
here. So that current can also be called as a conduction current.
Okay.
So
Understood.
that can happen even if it is DC or AC, right?
Okay. Yes. Yes.
Understood?
Yeah. By default, one if voltage different is there, that will flow. If
Yeah,
AC or DC, whatever. Yes.
yeah,
Fine.
correct. So the thing is, the conduction current has two meaning. Either it can be DC or it can be AC. So when I was
Okay.
discussing about the static fields, my conduction current is nothing but DC current because there is no time varying fields there, right?
Yes.
Whereas if you go for the time varying fields, the conduction current can also be in the form of time varying. That is happening because of the conductivity of the medium.
Okay.
Agree? Yeah,
Yes.
right. So the Ampere's law has been modified by curl of H is equal to the conduction current density plus displacement current density. So which is nothing but sigma E plus dou D by dou T. So if you see the comparison versus static fields versus our time varying fields, we'll write down what is the difference in the Maxwell's equation. Then it is easier to compare. So can you tell me one by one, what is the Maxwell's equations in static fields you got? Four Maxwell's equation. All of you, anybody? You can switch on your microphone and tell me. What is the Maxwell's equation we have studied in static fields? Four Maxwell equation. Anyone? Anyone can switch on your mic and click.
So,
Yes, yes. Tell me the first one.
first one is del cross E is equal to 0, means
So
KVL
curl of
actually.
electric, yeah, curl of E is equal to 0. Very good. And then second one.
Del dot T is equal to rho V.
Very good. Next one. This is called Gauss law. Third one.
Uh, del cross H is equal to J.
That is basically you can say it's a conduction density or DC current density. Next.
Del dot B is equal to 0.
Good. So what is the equations now we got modified? The first equation, how it is modified now when you time vary. So just now we have seen the curl of E is equal to the rate of change of magnetic field with respect to time. So this is what we seen in Faraday's law. So the time variation of magnetic field produces the space variation of electric field. And there is no change in the Gauss law. The second equation remains same and the fourth equation remains same. Because the nature of the magnetic field will be always rotational. So the divergence of the magnetic field will be always zero. So the second and fourth equation remains same and only the third equation is going to be modified. So right now, just now we have seen the third equation is modified by like this. Curl of H is equal to sigma E plus dou D by dou T. So this is called your displacement current density. So I can say the first equation also can be written as B is equal to mu H. So mu into dou H by dou T. And the third equation can also be written as sigma E plus D is equal to epsilon times E. So epsilon into dou E by dou T. Now, this first and the third equations are very important equation based on which we are going to discuss our next another 3 to 4 classes based upon these two equations. So what it actually says, you try to understand the meaning here. The time variation of the magnetic field is produces the spatial variation of electric field. So some simple example if I give. Suppose if you have a current carrying wire and you pass some alternative current through that. So when you pass any alternative current, you are definitely going to have a time varying magnetic field. So what you are going to get, because of time current you are passing through that, there will be magnetic field which will be generated like this in a azimuthal plane. And again using the first equation, whenever there is a time variation of magnetic field, it produces the spatial variation of electric field. So whatever the change in the magnetic field with respect to time, again is going to create an electric field. So you may have an electric field like this. So again, what happens in turn? Because this is time varying with respect to, that means the magnetic field is varying with respect to time, it is creating a space varying electric field. If the electric field is also varying with respect to time, what you will get? Again, space variation magnetic field will happen. So it's the reverse. That means the time nature, whatever the time variation of electric field or magnetic field is going to create a spatial variation of electric field and magnetic field. That's how your electromagnetic waves are created. So if you, another example I will give you, if we see the sources of electromagnetics, it is a simple nothing but an antenna. An antenna is going to create an electromagnetic waves. So first of all, how it is going to create an electromagnetic waves? So electromagnetic waves means which are propagating in space. So electromagnetic waves means those waves are propagating in space. But how does those waves are created is basically the time variation of the magnetic field and the time variation of the electric field. Now it is going to create your electromagnetic field was you are apply certain voltage across an antenna. So this antenna element is going to that means this antenna elements there will be some current flow through that. So because of this time varying field going to time varying magnetic field, the time magnetic field in turn will create your electric field using your first equation. That is how the electromagnetic waves are generated. So the basic reason why the electromagnetic waves are created, the fundamental principle is the time variation of electric field and magnetic field. And to keep it very simple, the time variation of current or the time variation of the voltage. That causes for the magnetic field variation. That magnetic field in turn causes for the electric field variation. So that's how you are going to create an electromagnetic waves which will be propagating. So with the understanding of how the electromagnetic waves are created, now we'll see the basic wave equations. Suppose there are different types of electromagnetic waves are there. Transverse electric, transverse magnetic, transverse electromagnetic. So we'll see all this type of electromagnetic waves later. And first thing, we'll try to obtain a wave equations. Based on the wave equation, we can see if any electromagnetic wave propagating in a certain medium, and you are going to analyze that. Analyze means there will be different thing. Suppose if the wave is traveling in any medium, what are the parameters you can analyze for that? First of all, you know the applications of the electromagnetic wave, right? In satellite communication, in mobile communication, in all the communication, you are going to send an electromagnetic wave and you are going to receive an electromagnetic wave. So the electromagnetic waves are carrying the information in the form of electric field and magnetic field. Now, to obtain the wave equations, first we will start with the time varying electric field as well as the time varying magnetic fields. So we will start with the basic two equations. So the first one, you are going to have the curl of E is equal to minus mu into dou H by dou T, and curl of H is equal to sigma E plus epsilon times dou E by dou T. So these are the equations we obtained till now. Now, for the understanding purpose, let us consider your electric field and magnetic fields are exponentially varying with respect to time. Okay, so definitely one parameter should be time varying. Then only it is going to create the spatial variation. So if you have time variation of magnetic field, then only it is create spatial variation of electric field. So I will start with electric field by assuming it's an exponential function. So something like this with respect to time, where omega is my frequency of the electromagnetic frequency which it is traveling. And the magnetic field intensity also, I can assume it as exponential function. And again, there is can you tell me anybody why I was considered as an exponential signal for electric field and magnetic field? Any guess? Can anybody say why I have considered an exponential function for both electric field and magnetic field? You know the answer or not? At least you can reply in the message. I was assuming electric field and magnetic field sinusoidal function. Correct, exactly. Because as I mentioned you, the sources of electromagnetic waves, simple example is an antenna. So the antenna is going to create an electric field which is said to be sinusoidal. Because whatever the voltage you are applying to the antenna is a sinusoidal. So every sinusoidal can be expressed as a combination of exponentials. So you got my point? So basically the electromagnetic waves are said to be sinusoidal. So sinusoidal is a combination of exponential. So that is I was assuming some electric field as some E naught e power j omega t. So E naught is electric field intensity at time t is equal to 0. So similarly, magnetic field intensity also I something like H naught into e power j omega t. So in your signals and systems, you would have been seen that. So when any signal is varying exponentially, you take the so if you take dou e by dou t, so what you are going to get j omega e naught e power j omega. So which means that dou e by dou t can be written as j omega times. So E naught into e power j omega t is straight away same as electric field intensity. So for all exponential signals, your dou by dou t can be replaced with j omega. So will you agree with my point? So from now onwards, I want to convert all the time domain into frequency domain by changing dou by dou t with j omega. So that is what you have studied in your signals and systems, right? Is it same or different? Okay, now you have to remember this point throughout the course now. So in our electromagnetics, wherever the dou by dou t term is present, from now onwards, I will replace it with j omega. Yes, so you have to keep that point in mind. So I will start with the first equation then. So you take the first equation and second equation. So rewrite those equations by replacing dou by dou t with j omega. So what is your first equation going to become? So curl of E is equals to minus j omega mu h. So let me call it as third equation. And similarly, your curl of h is going to become sigma E plus j omega epsilon times E. So I can call it as curl of h is equal to sigma plus j omega epsilon into E. I will call it as equation 4. Up to this, any questions you have? If you want to ask any questions, you can ask. So anything you have? So if you're okay, you just you can reply here. If you don't have any questions, you can reply here. No problem. I will proceed so that I can understand. Yeah. So the first thing is curve E is equal to minus j omega mu into h. And the other equation you got curl of h equal to sigma plus j omega epsilon into E. Right. Now I will apply one more curl on both the sides. So you can say minus j omega mu into curl of h. So if I apply curl on both the sides, what will happen? J omega mu is a constant and here it will be curl of h. So what is the expansion for this curl of E? So we know that that will be the gradient of divergent minus the Laplacian is equal to minus j omega mu into. So the value of curl of h you can replace with this. So that will be sigma plus j omega epsilon into E. So this time I want to test your understanding in static fields. What is the value of del dot E in source free regions? What is the value of del dot E in source free regions? Del dot E is equal to 0. What will be the reason? Can you explain why it is? No charge present. No, 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 no. I will give another. No sources means no divergence. There is a charge which is varying with respect to time. Suppose in that case, there is no current flow. Charge density 0. Now, still, you have not come to the some correct point. So the source free region means your rho v is equal to 0. There is no charge flow with respect to time. What you said was correct. But let me tell you in terms of mathematics only. So we have seen in the Gauss law. So what is the Gauss law says? Del dot D is equals to rho v. So when you don't have any charge, your divergence will be 0 straight away. And in that case, what we'll have del dot E epsilon times E is equal to 0 and del dot E is equal to 0. What you said was correct. The same thing I was proving it with mathematics, right? So whenever there is no charge in a source free region, your divergence of your electric field can be approximated to 0. So the first time I was considering it to be 0 by assuming that the wave propagates in a source free regions. So where there are no isolated charges. Fine. So in that case, what will happen? Your del dot E is equal to 0 and this minus and minus get cancelled. So I can write something like this. Del square E is equal to the whole term. I can put some constant gamma square. Yeah, any question you have? Ambrish Sarkar. Okay, no problem. So del square E is equal to, I was representing with some constant gamma square into E. Okay, this is my wave equation for electric fields. So where by comparing your value gamma square, I can call it as j omega mu into sigma plus j omega epsilon. So I will come back to this constant later. You take it as equation 5. So I will come back to this particular term later. So using this del square E is equal to some gamma square into some value E. You are getting that. And similarly, we can do the same thing for the magnetic fields. You apply curl on both the sides for this. So what will happen? So curl of H is going to equate it to sigma plus j omega epsilon into curl of E. Right? You go ahead, replace curl of E with minus j omega into H, and you proceed further. I was leaving an assignment to you. You find the curl on both the sides and you proceed ahead. You are going to get the same thing. So you are going to get del square H is equal to gamma square H. So I was leaving it to you and you can find it out. Just only expand this. You are straight away going to get this equation. Okay. Will you do or you want me to do? The second part. There is nothing is there. Only one step is there, which I have not done now. That's it. Yeah. So when you apply the curl, one more curl for the second equation, you are going to get the same equation. Del square H is equals to gamma square H. So these are basically called your wave equations. So these equations will define how the waves are propagating in different mediums. So there is another name for this. These are also called as Helmholtz equations. So these are basically said to be either wave equations or Helmholtz equations. So what we are going to do by solving the wave equation, we can see how the electric field and the magnetic field varying in a space. See here, suppose if you look at this particular equation, okay, what happens here? You know the value of gamma in a particular medium. Suppose if I assume that the wave is propagating in free space, you know the conductivity is 0 and mu will be 4 pi into 10 power minus 7 and epsilon value will be 1 by 36 pi into 10 power minus 9. So you know the value of gamma and then you try to solve for this electric field equation. So first take the integration for one time, you will get dou E by dou x and take the integration for the next time. You are going to define the equation for electric field and the magnetic field in that medium. So suppose if the medium changes, your sigma, mu and epsilon will change. So accordingly, again you have to solve the wave equations. So by solving the wave equations, you are going to get an equation for electric field and magnetic field in that medium. That is what the importance of the wave equations. Even you can remember this, I was going to use the same wave equation even if I go for the waveguides also, even in transmission lines. So till up to the waveguides, I was going to use the same wave equations to find out what is an expression for electric field and magnetic field for a wave in that medium. So you understood the importance of the wave equations now? Shall I go ahead now? Okay, anyhow, these wave equations we have seen already. Now we'll see a special type of wave, uniform plane wave. So the uniform plane wave is basically nothing but there are a particular characteristics for the uniform plane wave. It is also said to be transverse electromagnetic waves, which means that suppose if the wave is propagating in a certain direction, for the uniform plane wave, electric field is perpendicular to the propagation and the magnetic field is also perpendicular to the propagation. So I will write down the specific properties of that uniform plane wave. Your electric field and magnetic field are orthogonal to each other. And the second thing, the direction of wave propagation will be a unit vector along direction means it's always a unit vector. So unit vector along the cross product of E and H. Okay, some simple example I will give you, then you can understand this uniform plane wave. Suppose the wave is propagating in the Z direction. Okay, I have my electric field in X direction and I have my magnetic field in Y direction. Can I say this is a type of uniform plane wave? Can I call this as a uniform plane wave? The wave is propagating in the Z direction, but the electric field is oriented in X and the magnetic field is oriented in Y. Which means that this is your electric field vector. So flux lines are oriented in the X direction. And my magnetic field is oriented in the Y direction. So magnetic flux lines are oriented like this. So if you trace that, this gives the magnetic field. So can I consider this as an uniform plane wave or not? Yes or no? Yes, because you can see here electric field in X direction, magnetic field in Y direction. So both are perpendicular. So the first statement is satisfied. So when you say any uniform plane wave, both first condition you have to check was electric field and magnetic field are perpendicular or not. That you have to check. And the next thing, the direction of propagation. That means in this case, the wave is propagating in the Z direction. You can see here electric flux is directed along X, but the wave is propagating in Z. Similarly, the magnetic flux direction will be in Y and the wave is propagating in the Z. Right. So the wave is propagating. That means as the time advances, the wave is going to propagate along the Z direction. So if you see the Z direction, it is a cross product of your X and Y, which is nothing but your E and H. So that is also satisfied. So that's what you can see here. Even whatever our presentation, the first slide starts with this diagram. Because this actually gives your total electromagnetic wave. You can see here the wave is advancing in this direction. You can call it as a Z direction. So I can call this as a Z direction. And my electric field, you can see here, this is oriented along the X direction, but the wave is moving in the Z direction. So the flux lines are oriented in X, but the wave is advancing in the Z direction. So the red color, what you are seeing was your electric flux. And you can see here the magnetic flux here. Whatever the sky blue dot you can see here, this is your magnetic flux oriented in Y direction and it is advancing in Z direction. So any questions regarding the uniform plane wave? So for a uniform plane wave, electric field and magnetic field should be perpendicular and the cross product of E and H should represent the direction of propagation. So you understood the concepts, these two? Good. Now, we will solve the wave equation subjected to the uniform plane wave. And I would like to mention one point here. Whatever the waves propagating in free space, whether you are going for the satellite communication or your mobile communication, all those electromagnetic waves are of time, these are of transverse electromagnetic type. It's not a TE wave and it's not a transverse magnetic wave. So all the signals propagating in free space, use it for mobile communication, satellite communication, all are an example of the transverse electromagnetic wave. I will tell you how it is transverse electromagnetic wave. When you go to the waveguides, you will understand. But till that time, you can remember that any signal propagating in the free space, all the electromagnetic waves are of type transverse electromagnetic wave. Now, we will focus only on this transverse electromagnetic wave initially, then we'll go for the other type of waves. So when you solve the wave equations subjected to uniform plane wave, so let me start with the wave equations. So what is the first wave equation you have? Del square E is equals to gamma square E. So where your gamma square is nothing but j omega mu into sigma plus j omega epsilon. And similarly, you have del square H is equal to gamma square H. That I was not going to do. And I want the answers from you. How to expand this? Del square E represents what? Subjected to uniform plane wave. Now I already told you, uniform plane wave means example is like this. Electric flux lines are directed along X. Magnetic flux lines are directed along Y. And the propagation is along Z. Now, can anybody say how to expand this del square E now? Del is a spatial operator and you are talking about rectangular coordinate system. Now straight away del square E can be written as d square E by something. So what variation I have to consider here? How to expand del square E now? Yeah. Anybody? How to expand this del square E in terms of the differentiation? You can switch on your microphone. Why your class will be boring. If you are not answering, it will be completely boring. It is one-sided.
Sir, yeah, d square
Yeah.
e dx square plus d square e dy square plus d square e
Why it
dz
is
square.
xy? My point is that one only. If you are you are asking me to write d square e by dx square, of course, dou square and dou y square. Why these parameters are required here? If you see the uniform plane wave, in which direction the rate of change is happening?
X direction.
Is it x direction? Is it x direction? You see the uniform plane wave. Once again, you see this diagram.
In
See
z
here, you are
direction.
confusing. Electric flux lines are directed along x because suppose rate of change means, simple example, you can say for the wave amplitude variations. So in which direction you are finding the amplitude variations? You consider
Z
for electric
direction.
field, z direction. So which means that electric field is varying only in z direction. Understood my point? The flux
Yes.
lines are oriented along x. Fine, that is fine. But where the amplitude is varying, at z equal to 0, your amplitude is minimum. And when you reach some z equal to this particular point, your amplitude is maximum. So when the value of z changes, you are going to have a variation in the amplitude. So that is what you should mention it in the spatial variation. So I hope the point is clear, right? You should not
Yes.
consider x. X is the direction of the field. But the amplitude variations are happening when you are moving along z. Del means a rate of change, I told you in the first class itself. So in this case, what you have to consider right now? So when you are finding del square E is equal to gamma square E, I can straight away say d square E by dz square is equal to gamma square E. So still anybody had doubt? Can you tell me the magnetic field? Same way, del square H is equal to gamma square H. This is the equation you have. How to expand this now? If you want to see the diagram. If you want to see the diagram, how to expand? What is the variation? Rate of change is occurring in which direction for the magnetic field? Is it y direction? Z, correct. To see this point clearly. See, the magnetic flux lines are oriented in y, but the wave is advancing in the z direction. So when I say uniform plane wave and the rate of change, you should see here at z equal to 0, the magnetic field is minimum. And when you move to this particular point, your magnetic field is maximum there. So even for magnetic field also, the rate of change is happening only along z. You got the point? Everybody? This point you have to consider. Always you will confuse with the direction. Direction is different part and the rate of change is different part. Okay, the rate of change means, simple example, you can see the amplitude variations. So in this case for uniform plane wave, if the wave is propagating along z direction, your electric field also varying in z direction, magnetic field also varying in z direction. But the flux lines are oriented along x. You got the difference? You got the difference now, understood or not? You can reply here. Then I can go ahead.
Hello, sir.
Yeah.
So every time, whatever the direction of wave, that way we'll assume these things. That is del square E with z square.
No, see, direction is different. See, the flux is oriented in the one particular direction, but the rate of change is happening in other direction. That's what I was trying to convey to you. See, the flux is oriented in the x direction. That means the flux lines are directed along x direction. Okay. But when you see the rate of change, means amplitude. What
Yeah,
happens when you are
amplitude of
moving
wave.
along the x direction? Do you have any changes in amplitude? Will you be able to see? You are moving parallel to the flux lines, right?
Okay.
Yeah. So when you are able to observe the amplitude variations,
So we need to check always the wave, right? Means we need not check the E or H. We'll directly check the wave. That's it.
you directly come again. I am not able to understand because your voice is low.
Yeah, we need to check the wave only, right? We need not
You need to
consider.
check the wave. Either it will be amplitude variation or it will be a phase variation.
Yes, sir. As the wave is propagating in Z, so
Hmm.
its amplitude is varying in that direction. Okay.
Exactly. That is simple. You need not to think too much there. The wave is
Yeah.
propagating in the z direction, so you have the variations along z. That's it.
Yes.
Suppose, as an example, I will give you, and this is your x-axis and this is your z-axis. Okay. Suppose if the wave is propagating in this way,
Yeah.
so in this case, you should consider x variation as well as the z variation.
Yes,
Understood?
sir. Yes, sir.
So that's it. Simple. In which direction the wave is traveling, in that variation only you have the amplitude variation, right?
Yes, sir.
So that is a simple logic here. And so when you do this, now you can solve this differential equation. I hope you will be able to do that. And you solve the differential equation and tell me the solution for electric field. And I hope in mathematics, the differential equations part is over. Isn't it? So you solve this differential equation and tell me the solution for the electric field. Yeah. Then you will be able to do. So how to do that? D square E by dz square is equal to minus gamma square E is equal to 0. So you can write the differential equation something like this. D square minus gamma square into E is equal to 0. So what is the roots for this? You are going to get plus or minus gamma. Agree? So whenever you are having the roots like A comma B, can you tell me what is the solution? Some constant C1 into e power ax plus C2 into e power bx. I hope this will be everything will be clear for you. With that, I was proceeding it. So, yeah, any questions?
Clear, sir. Clear.
Yeah. Then can you tell me what is the value of electric field now? Because there x is a variable, but here our variable is z, right? So I can say electric field as a function of z as well as time. If you are writing it, how to write? C1 e power gamma z, because a is nothing but gamma and b is nothing but minus gamma, plus C2 e power minus gamma z. So this is the variation of electric field in z direction into time variation will be e power j omega t, because in the starting only we have discussed the electric field is exponentially varying with respect to time. And what is the direction? So the direction of electric field will be the flux lines are oriented in x direction. So that is what we have studied. If you see the equation, the electric flux lines are oriented in x. This is represents the direction part, but the magnitude variation is happening along z. So this is my equation for the electric field. Similarly, you can do the same thing for the magnetic fields. I can write the equation something like this. H of j comma t is equal to some constant C3 e power gamma z plus C4 e power minus gamma z. Same procedure, right? So you are going to get the same equation like this. E power j omega t into direction will be a by cap. So these two are very, very important equations which you have to remember forever. So these are the equation for your electric field and magnetic fields of a uniform plane wave propagating in any medium, like free space or any source-free regions you can consider. So these two represents the equation for electric field and magnetic field of a uniform plane wave. So this is very, very important. You have to remember.
Sir, could you just
Yeah.
repeat how did that e to the power j omega t ax cap come from?
No. First, you go back to our wave equations. What is the condition you have assumed there?
Okay, okay, sir.
First, initially, when I was solving this equation only, I told you, right? Electric fields are said to be exponential signals, right?
Yes, sir.
So that part I was adding it there. That's it, nothing else.
Fine.
So when you are considering about electromagnetic wave, it should be a function of space as well as function of time. Then only it is said to be wave nature, right? Excuse me, you got my point?
Yes, sir.
Yeah.
Yes, sir. Got it.
So, in other words, I can say is because the point has come here, in most of your interviews, they will ask what is the difference between a signal and a wave, right? I can say this is a basic difference. So you can say the voltage and current is basically said to be the signal. And when I consider electric field and magnetic field, I was calling it as electromagnetic wave. Can anybody tell what is the difference right now? Based on whatever the understanding you have, can anybody give some clarification? Voltage and current, you can call it as a signals. And electric field and magnetic field, you can call it as an wave, electromagnetic waves. So what is the basic difference there? You can see here, when I say any wave nature is having a multiple dimension variations. So which means that you can see here electric field and magnetic field not only vary in space, but also vary with respect to time. Whereas when you consider a voltage, so if you consider the voltage and current in your networks, it's a function of time only. So if it is a function of only one variation, you can simply call it as a signal. So the wave nature basically represents those parameters will have the variation in multiple directions. That means the electric field and magnetic field will vary with respect to space and will vary with respect to time. So that is the reason why you are calling it as electromagnetic waves. Fine. Yeah. Here now I have a basic question. You have to answer me. So sir, you said that the wave is happily propagating along z direction, and now you got the equation something like this: E of z comma t is equal to C1 e power gamma z plus C2 e power minus gamma z into e power j omega t into ax cap. So I have a basic question here. Suppose gamma is just basically a number. You forget about that. So let us say gamma is positive in certain applications. So in that case, what is this equation represents? So when gamma is positive, the first term represents your electric field exponentially increases with increase in z. And second equation represents your, because gamma is positive, so electric field exponentially decreases with increase in z. So does this equation represents amplification as well as attenuation? Do you consider in that way? Is my way of explanation correct regarding this? Suppose if you assume gamma is positive, this represents amplification and this represents attenuation. Do you think is that correct? Do you have any amplification of the signal once it propagated from one end to the other end? First thing, suppose when you transmit any signal, can you expect any increase in the amplification of the signal? Yeah.
It only gets degraded.
Attenuated. Or else it can maintain the same amplitude, right?
Yes.
Yeah, you can't get any amplification. So what is my way of interpretation? The way of how I was interpreting is wrong. Then what is this particular term then? So since you don't have any amplification as the distance progresses, what is this equation says then? So this equation, I want to know the answer. What is this equation says? The reality is something different and the mathematics says something different. So first of all, still there is a confusion. So the reality says that electric field should maintain its amplitude or else it can degrade. It can never get amplification. But your mathematics is 100% correct. But actually how it is was, see here, suppose if the wave is propagating in the z direction. What is this equation indicates was, this is your incident wave. Let me call it as an incident wave, right? The wave is propagating in the z direction. Now, I will put one metal in the space. The wave is happily propagating in the z direction and I kept a metal plate here. Can you tell me what will happen in that case?
Sir, it reflects.
Full signal will get reflected back, right?
Yes.
The wave propagates in which direction then?
Negative Z.
Yeah. Now can you tell me what is the meaning of this one? First term represents now? First term and second term?
So one is for incident and another is for reflect.
Very good, very good. That's what it says. Even though your gamma is positive, the first term will be present whenever you put any metal plate in the free space. So even though your gamma is positive, suppose your Z can become negative. In the same fashion, here gamma is positive means Z is positive. Which means that if you see here, Z is positive for the incident wave. So the second one is the incident wave. And your Z is negative for the reflected wave. That's it. So your mathematics is always correct. You have to believe that. But sometimes it can go wrong. But actually in this case, it is 100% right. So what is this equation says? The electric field in a space is the sum of the incident electric field as well as the reflected electric field. Now the point is clear for all of you. So this particular term represents the wave which propagates in the negative Z. So whatever I have written here, C1 e power gamma Z plus C2 e power minus gamma Z. If you assume gamma is said to be positive, so I can once again repeating here, you carefully have a look on this. So this term represents the wave which propagates in negative Z. And this term represents the wave which propagates in positive Z. So you can have two components for the direction of propagation, provided if you have any obstacle which will be blocking that electromagnetic wave. So if you place any metal plate in the medium where the waves are propagating, you are definitely going to have a reflected wave. So the first term is accounted for the reflected wave and the second term is accounted for the incident wave. Now for the simplification purpose, I was assuming that there is no metal plate and there are no reflections at all. So as long as you don't have any metal plate, you don't have any reflections. Oh, is my voice breaking?
No, sir. It's clear for me.
It's clear. Huh? Others? Others, can you check? Is my voice breaking or? Yeah, you can check voice is breaking. You can check your internet connection. Okay, fine. So if you are assuming that there are no reflections in the medium, that means there are no obstacles in the medium, how to write this equation then? The first part can be ignored, right? As long as there is no reflections, I can ignore the first part. So the electric field intensity is purely the second part. So what I was doing, assume there are no reflections. There are no reflections means the first term will be absent. So in that case, the solution of uniform plane wave is given by like this equation. E naught e power minus gamma z. So what I actually have C1 e power gamma z plus C2 e power minus gamma z. So if you don't have any reflection, first term will be 0. So whatever the constant C2, I was calling it as some initial amplitude at z equal to 0. I was defining it as some constant E naught into e power minus gamma z. And variation with respect to time is e power j omega t into direction will be in the x. So this is what we are assuming from the uniform plane wave. So similarly, the magnetic field intensity you can write the same fashion. If you don't have any reflection, the same equation will follow. H naught e power minus gamma z e power j omega t, direction will be a by cap. So these two represents the solution of uniform plane wave by assuming there are no reflections. Sense now? Is there anything wrong in these two statements? If I assume there are no reflections, is there anything wrong with the equations then? So if you're assuming there are no reflections, these two are the valid equations because your gamma is going to be always positive, and in that case, these two are valid. So any questions till now? You are free to ask.
Hello, sir. This one
Yeah.
is will be attenuated or amplification?
This one will be attenuated, right? That's what I was saying, right? Because in a uniform plane wave, you are assuming that the wave propagates in the positive z direction, right? Now I don't have any metal plate, so you don't have any reflected. So in that case, your gamma will be always positive. You can see here, root over j omega mu into sigma plus j omega epsilon, right? In this case, is there any term which is going to be negative? Will your
No.
conductivity is negative or positive? You won't get conductivity, permeability, and permittivity. All are a positive constants, right?
Yes.
So the propagation constant is always positive. So in that case,
Okay.
if gamma is positive, what is this term represents then?
Attenuation.
Right. That's what. So that is what it is matching with your normal theory, right? So when the wave is propagating in any medium, hardly you can expect there is no attenuation, or else the wave should attenuate. So there will not be any amplification.
Sir, hello.
Yeah.
In free space medium where
Hmm.
there will be addition of these two components, reflection
Addition of
and
what?
incident. This reflection and incident both will be always present.
Both will be
Means
present, provided if there is any obstacle, which means that there is any metal plate, something. If there is any obstacle is there, then reflection will be created. Now, as of now, I was assuming that there are no reflections. I will consider the reflection part in the next section. Okay, you got
okay.
my point? Yeah. So
Okay.
what will
Whenever
happen when
reflection, hello, sir. Whenever reflection present, then only that both
both will
attenuation
come?
and
It's not amplification; it's the reflection plus incident.
yes, that both are combined.
Exactly. Whenever there is any reflected wave, the total electric field will be sum of both the first term plus second term. Both terms will be present.
Okay.
Agree? And once again, I was telling, if there is no incident wave, there is no reflected field. Agree? Yeah?
Oh yes.
So either these two terms will be present or only the second term will be present. That's why it is. Somebody is saying, can
Okay.
we say that the value of C2 is E naught? No, that's what I have written here, right? Whatever the constant C2 I have called, it has some initial amplitude I was defining. So because this constant will be, when you put a Z equal to 0, you can say some initial amplitude will be there. So that I was calling it as E naught. Yes, the constant C2 can be considered it as E naught. Yes. So now you understood the concept of uniform plane wave, right? Any questions? I will give some examples. So let us consider an first example. So I have one electromagnetic wave, and which is a uniform plane wave. So the equations I was writing it something like this. You can see here.
Hello.
So I'm audible now. Still, I'm not able to. Yeah. So let us consider this example. So I have this electric field intensity equation, and have a look on this equation and tell me in which direction the wave is propagating.
Negative
Yeah.
y.
What is the answer? In
It's propagating negative y.